Today we are going to consider the confirmatory test of the cations, and if possible, we start with the anions. And when it comes to the confirmatory test, like I indicated the other time, it is one specific test to identify one particular cation. So it's just a single test which is meant for a single cation. So we pick them one by one, all the cations, and then we consider their confirmatory test. For the ammonium ion, yesterday, we did everything under that. Because for the ammonium ion, when you add the sodium hydroxide, ammonia gas is involved. And we can confirm the ammonia gas by dipping a rod in conch HCl. Then when it is brought near the gas, you see white fumes of ammonium chloride forming. So the dense white fumes of ammonium chloride which is formed as a result of bringing the rod dipped in conch HCl near the gas confirms that the gas is ammonia, and therefore ammonium ion is present. So for that one, that is how we confirm the ion. Now, when it comes to zinc, when you add aqueous ammonia to zinc in drops, what do you see? What will be the observation? Okay. When aqueous ammonia is added to zinc ion in drops, what will be formed? What will be the observation? Look, Brian.
In drops. So I'm asking, is it in drops? Are you talking about in drops?
Yes.
Oh, you see the white gelatinous precipitate.
When you add in excess, what will happen?
For zinc, it will be soluble.
It will be soluble. So in order to confirm zinc ion, we use aqueous ammonia solution. So we add the aqueous ammonia solution in drops. Then after that, we heat the resulting solution. So when you add the aqueous ammonia in drops to form the white gelatinous PPT, we don't add in excess to dissolve it. Just after adding in drops and the white gelatinous PPT is formed, the heat is applied to it. So when you heat the precipitate strongly, then there's going to be a decomposition of the precipitate to form zinc oxide. And the zinc oxide is yellow when hot and white when cold. I repeat, to confirm Zn2+, we add aqueous ammonia solution in drops. Yesterday, I explained that aqueous ammonia contains hydroxide ions. So when you add the aqueous ammonia in drops, it's going to react with the zinc ion to form zinc hydroxide. This is a solid, and this gives you the white gelatinous PPT. Now we don't add in essence. Then the PPT which has been formed is now heated strongly. And this substance will decompose to form zinc oxide and then water vapor. So water will be liberated. Now, the zinc oxide, which is a residue, is yellow when hot and white when cold. So with this, we will be able to confirm that the substance in question is zinc ion. Is zinc ion. That's the confirmatory test for the zinc. Now, another confirmatory test is by adding ammonium chloride followed by aqueous ammonia, and then hydrogen sulfide gas is bubbled through. And that's going to form a white PPT or zinc sulfide. So using hydrogen sulfide solution, aqueous, or the gaseous, or the gas, it will be able to react with the zinc 2 ions to give you zinc sulfide. The zinc sulfide is a white PPT. This one is white PPT. So you can use this one to also confirm the zinc. Now there's another reagent that can be used. That is potassium hexacyanurate 2. This chemical can also be used to confirm the zinc. And when this solution is added, it gives a greenish to white PPT. And that also confirms that the zinc 2 ion is present. So please, before you get to the confirmatory test, the preliminary test alone will give you a clue, will give you a hint that zinc is there. So any other subsequent test that you are performing is just to aid or to confirm the lead. So I want you to see it in that light. So for the zinc, we mentioned 3 tests there. The use of aqueous ammonia, followed by strong heating, and then the use of hydrogen sulfide, and that'll give you white PPT, and then the use of potassium hexacyanurate 2, that is K4FeCN3. It's a complex salt. It's a complex salt. Potassium hexacyanurate 2. This one. Now it's a complex salt. That can also be used to confirm the zinc. Then we come to lead, the next ion. For lead, we can use 4 different reagents to confirm it. Pb2+, can be confirmed using hydrochloric acid. When the HCl is added to the test solution that contains lead, you are going to form lead chloride as the crystals, and it is white PPT. With the release of hydrogen ions, you can balance the equation to that effect. Now, this white PPT which is formed is soluble when hot, and the crystals reappear on cooling. So, you have suspected a test reagent to contain lead, and you want to perform a confirmatory test on it. You can use HCl. When the HCl is added, you are going to form a white precipitate, which is soluble on heating and reappears or recrystallizes on cooling. Meaning that lead chloride is soluble at higher temperature, but insoluble at lower temperature. So when the white PPT is formed, PPT, the lead chloride, and you heat it, the PPT dissolves. The lead chloride PPT dissolves. On heating, and reappears, or if you like, recrystallizes on cooling. This confirms that lead is there. That's it. But apart from the HCl, we can use potassium iodide solution. When potassium iodide solution is used, that one is a reaction, of course. This is going to give you lead iodide, PPT. This one is bright yellow PPT. It gives you bright yellow. In fact, nice color, bright yellow PPT formed, which also dissolves on heating and reappears on cooling when you use potassium iodide solution. Then also, we can use potassium chromate solution, K2CrO4, aqueous. This one too is a reaction. So this is going to give us lead chromate, PPT. The lead chromate PPT is yellow. That one is yellow. This yellow is brighter than this. Even though this one too is yellow, there's a great difference between this yellow and this one. So this one too will give us yellow PPT, confirming the presence of lead. Confirming the presence of lead. Then the fourth one has to do with sulfuric acid. By using dilute sulfuric acid, you are going to form lead sulfate. And lead sulfate is insoluble. That's going to give you white PPT. White PPT of the lead sulfate. So when it comes to lead alone, we have 4 different reagents that can be used to confirm them. Yes, sir. Have you gotten it? And I hear you be brave.
Sir.
Hello?
Yes, sir.
Brian, what did he say?
I say yes.
He says okay.
Yeah.
Okay. Michelle.
Sir, please, yes, I said I had a question. Please, this identification of cations, is it only in the NOVDEC practicals it comes, or it comes in YC too?
Cool. It's everywhere.
Oh, okay.
Yes.
Okay.
So when it comes to the May, June, the school one, that one you do it, that one you perform it.
Oh, okay.
They'll give you the solution and they'll instruct you what to add and what to do. Then based on the observation, then you draw your conclusion or your inference. Now you perform it.
Okay.
End of deck, they can put it in the tabular form, and then certain things will be left out, and then you will fill it. They'll create some gaps, and then you fill in the gaps.
Okay.
So I'll be giving you some examples for you to see. But for the that one, you perform the practical.
Okay. Okay. Thank you.
Right. Now, when it comes to calcium, you can use sulfuric acid. And in fact, calcium with sodium hydroxide alone, you can confirm it. Because we know that for calcium, when you use dilute sodium hydroxide in drops, you are going to get quite chalky PPT. The PPT is insoluble in essence. With this alone, you can confirm the calcium. As for ammonia, it does not even react with it at all. So definitely, you perform the preliminary test before the confirmatory test. Unless otherwise, you cannot just jump to go to the confirmatory test. So usually, you perform the preliminary test before coming to the confirmatory test. So before you even get to the confirmatory test, you have an idea which ion is there. So the confirmatory test is to just add up to the whole thing, and then you are fine. So for calcium, we use sulfuric acid. So the calcium will react with the sulfate ions to give you calcium sulfate. If you know your solubility rules well, you note that all sorts of sulfate are soluble, except those of calcium, lead, silver, and barium. So if calcium is there and you're adding sulfuric acid, that reaction will be there to form the calcium sulfate. So that will give you quite precipitate. So that is how we confirm the calcium. That's how I confirm the calcium. Then when it comes to copper, now copper, when you add dilute ammonia solution in drops, what do you get? What will be the observation? Yes, Bob. Yes, we did it.
Yes, blue gel.
Can you qualify the blue?
Pardon?
Qualify the blue.
So please repeat the question.
I'm saying, you said blue gelatinous PPT.
Yes, sir.
And I'm saying that, can you qualify the blue? When you add dilute ammonia to a solution that contains copper 2 ions, it gives you light blue gelatinous PPT. That's what I'm asking for. Light blue.
Oh, okay.
Yeah, gelatinous PPT. Now, when you add in essence, what will happen? What will you see?
So it will be deep blue.
It will be deep blue.
Yeah. The PPT will dissolve, forming a deep blue.
Thank you. So when you add the aqueous ammonia, then the PPT dissolves, forming a clear deep blue solution, a very clear deep blue solution. That one alone is a confirmatory test. By using the dilute ammonia, even though it is a preliminary test, it is also used as a confirmatory test. Apart from that, we can use potassium hexacyanopherrate 3 solution. When you add it to the test solution that contains copper 2 ions, that's going to give you reddish brown gelatinous PPT. Reddish brown gelatinous PPT. So for that one, the complex is potassium hexacyanopherate 3. The one we use for zinc is potassium hexacyanopherate 2. Now the oxidation state of the ion is +2. But this one, the oxidation state of the ion is +3. And we can determine that. The potassium is +1. So we have 3 of them there, so that's +3. Plus the ion, we don't know. The cyanide, one is -1. And we have 6 of them there, so that's going to give us -6. This will be equal to 0. So X is equal to +6 minus 3. So that's going to give us +3. So that is the oxidation state of the ion. So in this case, you have potassium, the name I mean, potassium hexacyano. The cyanide is a ligand. So the name for that ligand is cyano. So potassium hexacyanopherate, the ion becomes ferrate. You use the Latin name. So the ferrate is obtained from ferrum. So potassium hexacyanopherate followed by the oxidation state of the ion +3. So potassium hexacyanopherate 3 solution. When you use that one, then you are going to form the reddish brown PPT. The reddish brown PPT. So it means that copper 2 ions can be confirmed in 2 ways. By using dilute ammonia in drops and then in excess, and also by using potassium hexacyanopherate 3. Now, when it comes to ion, we can use the potassium hexacyanopherate 3. That one will give us dark blue PPT. When you are confirming ion 2, Fe2+, potassium hexacyanopherate 3 can be used, and that one will give you dark blue PPT, very dark. If you don't take time, you might see it as though it's black, but when you shake it, then you see it to be blue. Dark blue PPT will be formed. But if you are using potassium hexacyanopherate 2, that one will give us white PPT, which will tend to dark blue on standing. So when you are using potassium hexacyanopherate 2, you are going to get white PPT. But when you leave it for some time, then the white PPT will tend to dark blue PPT, dark blue PPT. So when it comes to those transition metals, like I said, by their color, you know them. So the preliminary test alone is telling you that it is this ion which is there. So the confirmatory test is just an added test to be sure that it is that particular ion which is there. Okay, so when it comes to the transition metals, talking about Fe2+, Fe3+, Cu2+, I would like to include it with Zn2+. Those ones, I will summarize their test and I'll forward it to you so that it will be easier for you to easily memorize them. Yeah. Any question? No question.
No, sir.
Yes, sir. Hey,
Sir, I said no.
Chief.
Hello, sir.
Yeah. Abby.
You're cool.
You were chilling small.
Oh, sir, no. I have to do something for the family.
Okay. Welcome.
Thank you, sir.
Right. So if you don't have any other question, then I'll move on to the identification of anions. The anions. Now, when it comes to the anions, we'll be considering carbonate ion, sulfite, sulfate, sulfite, nitrite, nitrate, and then the halides. The halides. Chloride, bromide, and then iodide. Yeah, these are the anions. 9 in number. 1, 2, 3, 4, 5, 6, 7, 8, 9. The cations are 8 in number. When it comes to the anions, they tend to give off gases. So, when the gas is coming out, yesterday I mentioned 3 things that you have to observe when a gas is involved in a reaction. Who remember those 3? The 3 things that must be observed when a gas is producing or when a gas is produced in a chemical reaction. What are the 3 things you have to note when a gas is involved in the course of the test? Ken, do you remember?
Sir, please no.
Oh, are you sure? When the ammonia gas was coming out, there were certain 3 things were observed about the gas. Oh, okay. Who remembers it?
Sir.
Yes, sir.
Sir, I just remember the some 2 things: the color and the smell.
The color, the smell,
And the smell of the gas.
Then there's another thing.
I don't remember the 3rd one.
Okay, Michelle. The 3rd thing.
Say it turns wet litmus paper red or blue.
Blue. It will change the red to blue.
Yes, blue. Yes.
Point is that when a gas is coming out, they need to know the color of the gas. It gives you certain information about the ion present. You need to know the odor. That's the smell. And then the 3, the effect on litmus paper. As to whether the gas is acidic gas or basic gas. So when it comes to the anions, they tend to give off gases with the exception of sulfate. SO42 minus. That one alone doesn't produce off gas or doesn't give off gas. Just like the cations generally do not give off gases except ammonium ion. When it comes to the anions, all the anions tend to give off gases except the sulfate ion. That one do not give off gas. Now, when it comes to the anions, the reagent that are used for the preliminary test is either HCl or HNO3 or sulfuric acid. Mostly this and this are used. But occasionally this one too can be used. So these reagents are for the prelims, for the preliminary test. Then other reagents that can be used include barium chloride or barium nitrate. This can be used. We can also use silver nitrate solution. All these are in the solution form. And sometimes lead nitrate. So the reagents used in testing for anions is clear. It is very clear. So if you are using this reagent and you are recording cations, then it is a sign that you don't do anything. These reagents are used for testing anions, So I'm going to use the HCl or the HNO3 on all of them to see what will happen. So we have our test. Observation. And then our inference. So let us assume that we are giving solution A. No, let's use solution C plus dilute HCl. Aqueous. If this one is there, then there's going to be effervescence. Effervescence. Odorless. Colorless gas evolved. The gas turns, yes, so as soon as you add HCl to a test solution and there is effervescence, odorless, colorless gas evolving, and the gas, when bubbled through lime water, turns the lime water milky, that means that the gas is CO2. Therefore, CO3 2 minus is present. And I hope you know effervescence. Effervescence is like when you open a mineral, as if it is boiling, sort of. Let me see whether I can show you. This is HCl. I'm applying it on solid sodium hydrogen carbonate. It contains the carbonate ion. Look at it. Did you see it? It fizzes. It's like it's boiling, sort of. That is effervescence. That's effervescence. So when you add HCl to a test reagent, and there is effervescence, odorless, colorless gas evolving, and if the gas turns lime water murky, that means that carbonate ion is present. Please, at the inference column, we are recording that the gas is CO2. CO2 is not an ion. CO2 is not an anion. The anion in the sample is carbonate. But it is the CO2 that is assisting us to confirm that the carbonate ion is there. So you don't write that the gas is CO2 and then full stop, you leave it like that. No. The gas is CO2, therefore CO32 minus is present. Understood? And that is how we test for carbon dioxide gas in the lab. That's the confirmatory test. Any question there? No question. Now come to the B. I'm moving on to the SO32 minus. If you have a solution labeled C, the test solution labeled C, and it contains sulfite, and you add dilute HCl, to it, a colorless gas will be evolved if the SO32 minus is there. A colorless gas with a pungent smell. Pungent smell is evolved. Here, the gas which is evolved is actually SO2. And SO2 smells like a strike match. You know, when you strike a match, see, it has some peculiar scent. That is how pungent smell is. So the gas which is evolved, when it is bubbled through acidified KMNO4 solution, it decolorizes the purple color of the acidified KMNO4 solution. Because the gas which is there, that is the SO2 gas, is a reducing agent. So when it is bubbled through the acidified KMNO4 solution, the color disappears. It reduces the Mn from +7 to +2, which is colorless. So the gas, when bubbled through acidified KMNO4 solution, I'm representing it this way. KMNO4 stroke H+, meaning acidified KMNO4 solution. The purple color of the solution disappears, or it becomes colorless. Now, at the inference column, you say that the gas is SO2. Therefore, SO32 minus present. Do you follow it?
Yes, sir.
Great.
So please, I have a question.
Yeah, go ahead.
So when you say bubble through, like, please, how is it done?
Huh?
No. You said the gas is bubbled through the KMNO4.
Okay.
So I'm asking, like, so how is it done? I don't.
You don't understand the term bubbled?
Yes, sir.
Oh. Okay, let me illustrate that. Assuming this is your test tube, assuming this is your test tube with a delivery tube on it. Okay? So when you pour the acid onto the test reagent and the gas is coming out, so the gas can pass through the delivery tube. So if this is KMNO4 solution, you put the delivery tube in the KMNO4 solution. Okay? That's what we mean by bubbling the gas through the KMNO4 solution. So the delivery tube dipped into the acidified KMNO4 solution. So you see something like this. Aha. So the gas is bubbled through it. That's the meaning.
Oh, okay, sir. Thank you.
Yeah. Now, assuming the gas is bubbled through alkaline solution or KMNO4 in alkaline medium, what will be the observation? If the SO2 gas were to be bubbled through KMNO4 solution in a basic medium, not in an acidic medium, what will be the observation? We have done redox, Mimperov. Mimperov. Michelle?
Sir, please. I'm not sure. I know it will become MnO2, manganese oxide.
Thank
but
you. But what will you see?
Yes, I'm not sure of that, but I think you see a brown precipitate.
Yes, Madam Sir. You see a brown black PPT of manganese 4 oxide, the MnO2. Because in a basic medium, the KMnO4 solution will reduce to MnO2. MnO2. Now, what will happen if the gas is bubbled through acidified potassium dichromate solution? Acidified potassium dichromate solution. Who's answering me? If the KMnO4 solution, if the gas is bubbled through acidified potassium dichromate solution, what are you going to observe? Chief?
So please, I don't think I know the answer.
Chief has given up. King? I love these two guys.
Say please. I'm not. I don't know.
We have done redox, so this is redox reaction. Yes, sir, Bob?
So,
Yes, sir.
please, I'm there. I don't know.
No. Okay, Michelle again. Let me see whether you're on top of your redox. Michelle?
Sir, please, I don't know.
Well, you remember we gave this one, that table, reducing agent and their oxidized form, oxidizing agent and their reduced form. If you bubble the gas through acidified potassium dichromate solution, it turns the orange color of this solution to what color?
Sir, can you please repeat?
Huh?
That I didn't hear you. Can you please repeat?
What I'm saying is that when you bubble the gas through acidified potassium dichromate solution, it turns the orange color of the potassium dichromate solution to green. The chromate or the chromium in the potassium dichromate is +6, and that is reduced to Cr3+, because the SO2 is a reducing agent. It is a reducing agent. This acidified potassium dichromate solution, we added sulfuric acid to it. That's all. That's the acidified potassium dichromate solution. It is orange in color. When you bubble the SO2 gas through it, any reducing agent, when you add it to this substance, the orange color you are seeing will turn to green. That means that the substance being tested is a reducing agent. So when the gas is bubbled through, in fact, even the SO3 minus, when you add it to it, it will turn green. Because this one is a reducing agent. It will turn green. And that shows that the gas is SO2. Therefore, SO3 minus is present. That's how we confirm SO2 gas in the lab. So we could use acidified potassium dichromate solution. The orange color will turn to green, the presence of the SO2 gas, or acidified potassium permanganate solution, which is purple. I hope you have seen that one before. Have you seen it before? Chief, have you seen it before?
Sir, please, no, please.
Kashibi. Michelle, how about you?
Please, what did you say?
This potassium permanganate solution, you see the color? So nice. It's purple in color. So if you add the reducing agent to it, it will turn to colorless. It will turn to colorless. It will turn to colorless. Let me see whether this will work. So I have acidified the potassium dichromate by adding sulfuric acid. I have acidified it. Let me add a substance to it and see whether it will reduce it. If it reduces, then the substance is a reducing agent. Oh, this one couldn't do it. It couldn't do it. But you can see that the color is changing. The acid is not enough. So if it is a strong reducing agent, like it will just go to colorless, direct. And if it is this one, the potassium dichromate, have you seen that it has changed a little? Have you seen that's changed? This is not what you started with. It is alcohol that I was adding. pure ethanol. And ethanol is a reducing agent. It's a reducing agent. This I think the acid is not enough. Otherwise, it should turn to colorless. It should turn to colorless. Yes. Good. Then we come to the SO4 2 minus. That one, he said, doesn't produce a gas. It doesn't give off a gas. So we move rather to the S2 minus. Now, if you have a test solution that contains S2 minus, and you add dilute HCl to it, a colorless gas with a bad, rotten egg smell, bad, rotten egg smell is evolved. A bomb can. Like, have you smelled rotten egg before? Yawa.
Yes.
A bomb. And it's a chemical reaction. That is, the hydrogen ion will combine with the sulfide in the solution to produce hydrogen sulfide. This one, this gas. And it's poisonous too. It is acidic. It's an acidic gas. If you turn red litmus paper, blue litmus paper red. So immediately you perceive this bad rotten egg smell, it means that S2 minus is present. In fact, the gas is H2S. Therefore, S2 minus present. S2 minus present. Neat. That is about the S2 minus. Now, when it comes to this NO2 negative and NO3 negative, if you add HCl to a test solution that contains the NO3 negative, there will be no observable reaction. There will be no gas evolved. But when you heat it, when you warm it a little, then a brown gas will be evolved. A brown gas will come out, which is acidic. It will turn wet blue litmus paper red. But the NO2, if that is what is in the test solution, and you add the HCl, the brown gas will come out without warming. So that's how we can differentiate between these two. For the NO2 minus, if that is what is in the test solution, as soon as you add the HCl, the brown gas will be evolved. But if it is NO3, there will be no observable reaction, there will be no gas evolved until you warm it. When you warm it, the NO2 gas will be evolved. That's how we do this one. For these ones, we usually don't use the acid on them. Because when you use the acid on them, you are going to get HCl, HBr, HR. That's all what you see. So that one, it doesn't actually give off any gas. So we don't see any observable reaction. However, chlorine gas, CL2 gas, is green. In fact, it is pale green. Bromine gas is brown. And then iodine, I2, is violet. Violet, is that how we spell it? Or it is VIO? Is it VION? Hey, please help. Or that one rather is wrong. Michelle?
That's correct.
Okay. It is violet, eh? Thank you. Please. Chlorine gas, bromine gas are all acidic. They will turn wet blue litmus paper red. After that, they will bleach the paper. So when you pass chlorine gas over wet blue litmus paper, it will turn red. Then in a few minutes time or seconds, it will become whitish. It will bleach the paper. Chlorine gas will do that. Bromine gas will do that. They all bleach litmus paper. So bromine, which is brown, and NO2 gas coming from the NO2 negative, and then the NO3 negative, these ones, they also generate some brown gas. The gas that comes out from that one is NO2. NO2. NO2 is brown. Bromine gas too is brown. The difference between these two browns, the bromine one will turn wet blue litmus paper red. After that, bleach it. But NO2 will not bleach the litmus paper. So with this, you can establish the two different gases and the source. And that's it. So what you have done here is a preliminary one. That is when a gas is being evolved.
Sir,
Yes, madam.
so please, for the chlorine, bromine, and iodine, how do you write it in the table?
No, that one will come to that test separately.
Okay.
Yes.
Okay.
Just a minute. All of it. Yes. Okay, no, bro. Now, when it comes to the specific text, the carbonate, the sulfite, and the sulfate go together. Now, in testing for those ions, we add barium chloride solution or barium nitrate. Barium chloride or barium nitrate. Any solution with barium in it. If these ones are there, you are going to get white PPT. Please, this one, it is anion. Anions, we don't qualify the white. When it, for the cation, that one you qualify the white so that you know whether it is zinc and aluminum or lead and calcium. So we qualify the white with gelatinous and chalky. But for the anions, we don't qualify the white. We don't qualify it. So when you add barium chloride to a test solution that contains carbonate, that contains sulfite or sulfate, you are going to get white PPT. So at the inference column, you record CO3 2 minus or SO3 2 minus or SO4 2 minus percent. Please, this test is specific for these three ions. So if you add a barium chloride or the barium nitrate and you don't see white PPT, then these ions are absent. The test is specific for carbonate, sulfite, and sulfate. So when you add the barium chloride or the barium nitrate or barium nitrate solution, and there's no white PPT formed, no observable reaction, then carbonate, sulfite, sulfate, absent. You record the negative text for it, because the barium chloride or barium nitrate is specifically for these three ions. Okay.
Yes, sir.
Thank you. Now, to differentiate between them, we add plus HNO3 aqueous. If carbonate is there, the PPT will dissolve. PPT dissolves with effervescence, odorless, colorless gas evolved. Then it means that carbonate is present. If PPT dissolves with a colorless gas with pungent smell, then which ion will be present? Then in this case, SO3 2 minus is present. Now, if the PPT is insoluble, then it is the sulfate which is present. So by using the HNO3 or HCl, this one can be or HCl, we can differentiate between which of the ions is present. If it is carbonate which is there, the PPT will be soluble, the PPT will dissolve with effervescence, odorless, colorless gas evolving. But if it is the sulfite which is there, the PPT will dissolve, all right, but a colorless gas will be evolved with the pungent smell due to the SO2. We did that one earlier. That means that SO3 2 minus is present. But if the PPT did not dissolve, the PPT is insoluble, then it's sulfate. Sulfate doesn't give off a gas. You remember? So that one will be present. Understood?
Yes, sir.
Any question on that? No question. Chief, echo you.
Echo you.
All right. So that's how we can differentiate between these ones. So please, among all the anions, it is only these three that we use barium chloride or barium nitrate in testing for. We don't use barium chloride for these other ions. No. We don't use barium nitrate for the other ions. The barium nitrate of the barium chloride is specifically for these three. So that is why I have intentionally arranged the ions there like that. It's for a reason. And the way I have arranged them there at the top there helps me to be able to identify them easily. I don't know the method that will work for you, but you have to devise means and ways of knowing the thing. In fact, what I'm teaching you, if you know it off head, when if you come to the main practical, you'll be fine. You'll be fine. Yes, because once you know it, it just flows like that. See, these two will be moving together. We'll be treating these two together. And this and this, that one to treat them together. So when it comes to the anions, you see that it's plenty. But it's not a problem. It's not difficult. See, out of the 9, we have handled 3 already. This one is so unique. The rotten egg smell alone is unique among all of them. This one, there's a test known as brown ring test. That's what we are going to use on them. Then the last 3 will be using silver nitrate to identify them. And the silver nitrate is purposely for the chloride, the bromide, and then the iodide. We'll look at that one. And you realize actually the ion cell and your thing. But please, if you don't know it, it can be frustrating. You'll be there. You miss the thing. You see something, but I don't know what to write. But if you have a fair idea, and usually the teachers will not take time and go through with it like this. I'm telling you, that one. So, but if you have a fair idea of it, and you are doing it, you enjoy it. You enjoy it. You can give me some iron. I can design a whole this thing on it. I know what to add, what not to add, and what you are expecting. So when you master it, it becomes so easy. Yes. So I'll not give you overdose. Otherwise, you'll be annoyed with me. So pause here. Then at our next meeting, we'll finish with the rest. And then we'll continue from there. Is that okay?